Alright, silly people, here's the situation. All we're doing is we're deriving the unit vector conversions um, from from circular coordinates to Cartesian coordinates, and then finding the time derivatives of the r and phi hat unit vectors, and matching what they got in the book. So, um, let's get started. So, interesting thing to note about any vector is that you can decompose it um, as being itself dotted with a unit vector that you want to represent it as times that unit vector um, for all unit vectors that you want to represent it with. So r hat is equal to r hat dot x hat times x hat plus r hat dot y hat times y hat. Um, so that's pretty awesome. Um, so really, this is just about finding out what r hat dot x hat is and r hat dot y hat is. So that's not too difficult because you know that the definition of a cross product between two vectors a and b, or it's a dot product, a and b is just the magnitude of a times the magnitude of b times cosine theta, where theta is the angle between them. In this case, the angle between r hat and x hat is phi. So, and then the angle between r hat and y hat is 90 minus phi. So we can represent r hat as being cosine phi x hat plus um, cosine phi minus 90 y hat. And then using just the definition of sines and cosines, you find that it's this. So that's pretty awesome. Now we need to find what phi hat is. Um, for that, we can use a couple different relations. The first is that you know that r hat has to be perpendicular to phi hat. So r hat dot phi hat is equal to 0, which means if we know what r hat is in terms of x and y, so we can write it in vector form, cosine phi, sine phi, and then when you dot that with phi hat, which also can presumably be represented in x hat and y hat with some unknown coefficients phi x and phi y, that will be equal to 0. So phi x cosine phi plus phi y sine phi is equal to 0. Um, and we'll use this to go ahead and partially solve for phi x. So it's going to be minus phi y tangent phi. Okay, there's another relationship that we can use. If we take the dot product of phi hat with itself, it better be equal to 1. For all unit vectors, that is the case. Um, so we're doing phi x, phi y, dotted with phi x, phi y, which is phi x squared plus phi y squared is equal to 1. We can substitute our expression for phi x into this equation and call it phi y squared tangent squared phi plus phi y squared is equal to 1. And then solve for phi y squared, which is going to be 1 over tangent squared phi plus 1. Yeah, okay. And then to put this in a nicer form, we can say multiply the top and bottom of that equation by cosine squared phi So you'll have sine squared phi plus cosine squared phi on the bottom. And then sine squared plus cosine squared is 1. So you just have cosine squared phi, so phi y is equal to cosine phi. Plug that into our expression for phi x, and you get minus cosine phi tangent phi, which is just minus sine phi. So now we know that the unit vector in the phi direction can be represented as minus sine phi x hat plus cosine phi y hat. Okay. What if we wanted to take the time derivatives of the unit vectors in circular coordinates? Well, we're going to need to do a little bit of product rule and a little bit of chain rule. So you're looking at first times the derivative of the second, so cosine phi dx hat dt plus second derivative of the first plus first derivative of the second, so sine phi dy hat dt plus y hat d sine phi dt. That's the product rule done. So the time derivatives of the Cartesian coordinate unit vectors are all 0. So we can go ahead and knock all of those guys out. Bam, bam. And then the time derivatives on the trigonometric function is going to be turned into partial derivatives. So we're talking about doing x hat d phi dt del cosine phi del phi. It's just a invocation of the chain rule there. Then this is d phi, d phi dt del sine phi del phi. So both of them have a d phi dt on it, which I'm going to label phi dot. And then you have x hat, and then the partial derivative of cosine with respect to phi is minus sine phi, and then you have cosine phi for this term. So notice how that is exactly equal to phi hat. So we've recreated a proof, or we've come up with an alternative proof for one of the proofs in the book, that dr hat dt is equal to phi dot phi hat. And then if we wanted to do d phi hat dt, much the same process. So time derivative of the minus sine phi x hat plus cosine phi y hat. Skipping the product rule stuff, just skipping straight to minus x hat d sine phi dt plus y hat d cosine phi dt equals minus x hat d phi dt del sine phi d phi plus y hat d phi dt del cosine phi del phi. Alright, oops. Okay. Factoring out phi dot again, you have a minus x hat, you have a cosine phi, you have a minus y hat or sine phi. Yep. Factoring out a minus sign, it becomes easier to see that this is exactly equal to, or the stuff inside the parentheses anyway, is exactly equal to r hat. So we've created another proof for d phi hat dt. So you go to minus phi dot r hat. All right.